Okay, welcome to RTOP December. Currently the Western Conference, Owens Valley, it looks like they were trying to negotiate a new contract, and all the negotiations went right into the time period that we were trying to get them to commit to, and they bowed out. Right now, we're either going to have a full Zoom or Deep Space Exploration Society might be able to pick it up. They're going to let us know next week. So they're in Colorado. Bill Miller is one of the key figures there. It may or may not happen there, but either way, we're going to have a Western Conference on Zoom. And we just may have it. The other place would be in Colorado at Haswell, and that's where the big 60-foot dish is in Colorado. Okay. Let's see who else. Let's go with Edward.
Hello, hello. Let's see. Is my camera working? Yes, it is. Okay. Can you hear me?
Yeah, go ahead.
Good. So, yeah, I've been quite busy actually lately with all sorts of radio astronomy things. So, I've been doing some observations again of the Andromeda Galaxy and another galaxy, IC342, with my 3-meter dish at 1420 megahertz. Still working on the data processing, so I'll report on that later. I am also working on a video about Andromeda, so expect it to drop sometime soon, perhaps next week or the week thereafter on my channel. So there's another thing that I've been doing. I've been doing some observations of water maze Westerhout 49. I can actually show you something of that. So let me share my screen. Oh, sorry, it's kind of tricky sometimes. All right, there we go. So I've been doing water mazer observations at 22 gigahertz with my 1-meter dish for a couple of years by now, as many of you may know. And I've been particularly interested in one source known as Westerhout 49 or W49, which is a star-forming region, and it hosts some of the strongest and most variable water mazes. So it's a very interesting source to do longer-term observing program on. So I've been trying to take a spectrum of this source once every 1 or 2 months. So this was during my most recent observation session on November 26th. So here you can see my IF average screen. And usually I'm just recording 1-minute integrations for about 30 minutes. And then later on, I average them afterwards after correcting for the frequency drifting of the LNB, because my LNB is not very stable in frequency. So you can see also that this is not bandpass corrected. I will always do that afterwards, so you can still see the bandpass shape of the SDR. In my case, I'm using an AirSpy. The little spike over on the left, that's just the frequency reference signal that I use to correct for the frequency drifting afterwards. But the interesting thing is the small bump in the middle, which is the actual water mazer itself. And it's quite unusual that you can see it so clearly in single 1-minute integrations. So I was already, this was already a sign that something unusual was going on. So these are my spectra from the past 4 months, from August onwards. So the vertical scale is not calibrated to Jansky because I don't really have any reliable way to do so. So this is all kind of qualitative. But still, you can see that there's quite some dramatic change in the spectrum. So you can see that especially the feature at minus 6.9 plus 6.9 kilometers per second, I should say correctly, of course, that has increased quite dramatically in brightness, whereas the group of features kind of at minus 10 to minus 4 kilometers per second, that has mostly remained the same over the past few months. So definitely something very interesting going on. So at the moment, Westerhout 49 is very bright, interesting to follow this potential flare event. And so for anyone who has a dish capable of doing observations at 22 gigahertz, is definitely a very interesting time to observe this particular source. Okay, so Yeah, before I forget to mention, I think Wolfgang from Astropilot is also on the meeting today, so maybe he'll show their observation, but they also observed this source recently, and they confirmed that they also saw a approximately twofold increase in brightness of the brightest feature with respect to their previous observation in October. So that was a nice confirmation for me to see that I'm actually seeing something real happening here. Anyway, so that was from the maser. Then there's something else I've been working on off and on for the past few weeks. So recently there's been a lot of discussion on the Sarah forum about interferometry, and this was kind of sparked by a post from Jan Lustrup. I think Jan is not on the meeting today, but anyway, Jan showed some very impressive results of his two-element interferometer. So he has 2.5 meter dishes, and he was apparently able to detect sources as weak as 10 Jansky, which is really impressive. But he also mentioned that it was sometimes quite difficult to tell apart different sources, because sometimes you have like two sources that are within the main beam of the elements at the same time. And then the fringes from these two sources can overlap, and that's can be very difficult to tell apart. And the second thing that was kind of difficult was determining the fringe period or the fringe frequency. And the fringe frequency is very useful for determining the declination of the source, which can really help in identifying what source you're actually seeing. I don't have an interferometer yet, at least, but I am very interested in this topic, and maybe I do want to build one at some point in the future. And it got me thinking about some clever ways we could maybe do data processing on the fringe data to improve our detections and source identification. So I was recently reading up on the KU band interferometer at Astropilot, and they used FFT analysis on the fringe data to kind of pull especially these weaker sources out of the noise, and also to measure the fringe frequency and calculate the source declination, or at least confirm that the fringe frequency matches the declination where the dishes were pointed at the moment. So then I started to think about how am I going to test this for myself, if this would be a useful technique, or under which sort of circumstances it can be useful. So I started to write a simple model in Python. I was just assuming a very simple two-element interferometer, so two elements on a simple purely east-west baseline, just looking to the south. And so this was the first simulation I did. This was just 10-meter baseline at 1400 megahertz and a source at the celestial equator. And here I was assuming that both of the elements are essentially looking at the entire sky. So here you can see the fringe frequency or the fringe period increases until you have the source transit, of course, and then it decreases again. So this has to do, of course, with the fact that the source is moving across the sky due to the Earth's rotation. So this is also what Earth rotation synthesis is based on. So I then ran a sliding window FFT. So instead of going to painstakingly program all of this myself, I used a program that I already had installed on my laptop from my geology degree. So in geology, there's a program called A-Cycle, and that is used for time series analysis of geological data. So for example, when geologists want to find certain cyclicities in their data, they use this. And there's all sorts of nice tools for FFT analysis and filtering and wavelet analysis. And I already had this, and I could just put in a text file and do these type of FFT plots. So that was really nice to use it this way. So here you can see what the sliding window FFT looks like, and you can see this arc in the fringe frequency due to the Earth's rotation. Of course, in a real interferometer, both of the elements, of course, have a certain beam width. So here I was assuming a 10-degree beam width, and then you are essentially only sampling a very small portion of this arc. So you don't really see the change in fringe frequency due to the Earth's rotation. So then I was coming back to the initial point of doing this, and that is, can we actually distinguish sources that are at different, at least at different declinations? So if you have two sources within the beam that are at different declinations, they should have different fringe frequencies. So you should be able to tell them apart from the FFT analysis. So this was a simulation with two sources at declination 0 and declination +5. And yeah, as you can see, it just still appears as one source. So this, of course, has to do with the fact that close to the celestial equator, the change in fringe frequency as you go to higher declinations is very small, because the fringe frequency and the fringe period are related to the cosine of the declination. So at low declinations, this technique is more or less useless. You go to higher declinations, it becomes more interesting. So this is the case for two sources at +60 and +65 degrees. And the fringes look kind of weird already. So it looks like we have three sources. So there's kind of two apparent sources flanking a brighter one. But actually, it's just two sources, and you can quite clearly see that in the sliding window FFT analysis. Of course, this has its limits. So if I do this with two sources at +60 and +62, then again, we cannot separate them unless we go to a longer baseline. So this is with 20-meter baseline, and then you can actually kind of start to tell them apart again. In real world scenarios, of course, we have usually have a bunch of noise, and yeah, our fringe data is not going to look very pretty. So I kind of try to simulate that by adding just random noise with the peak-to-peak amplitude that was 5 times the amplitude of the fringes. So you can still kind of see the fringes in the simulated fringe data, but it's very difficult to see them by the eye. If you run the FFT analysis, it still pulls out this this fringe signal. So seems to work quite well. Of course, this also has its limits. So this is with double the double the noise amplitude, and here you can still kind of see the fringes, but it's not very convincing anymore because there's also many false positives around. However, because we have a limited beam width, we are only sampling a limited range of declination. So there's also a limited range in the expected fringe frequency. So we can filter for that. Then again, we have a much better signal. So this is also a potential technique maybe to increase the to improve our detections. Anyway, so then I got into contact with Mike Ott, who was also working on interferometry, and he wanted to see if this technique would maybe be useful for his data. So he sent me some data from the Crab Nebula, Messier 1, Taurus A. So it's very nice fringes here. So this is a 2-3 meter dishes at a 30-meter baseline. And yeah, unfortunately, there is some RFI here as well. So these pulses are perhaps from aircraft radar, and you can see they also have an effect on the sliding window FFT analysis. So that's something to keep in mind. That's apparently RFI has quite some effect on this. So I then made a spectrogram of the fringes, just like from the part where you have the fringes from Taurus A alone. And here you can quite neatly see that the fringe frequency is 0.58 cycles per minute. So if you calculate the declination from that, you end up at a source declination of 22.0 or 22.7 degrees, whereas Taurus A is actually at 22 degrees, which is pretty close, I would say. So definitely close enough to be somewhat useful. Anyway, that's all I had for today. Are there any questions or remarks?
I have a question. When you collected that data on the water maser, you feel like you're very consistent in your receive setup, so that some of that variation is not just from maybe something's different in your receiver from one time to the next.
So essentially, I've not changed the water maser system in quite some time. So, and in addition to that, of course, you will have some variation due to like slight pointing errors and variations in the amount of atmospheric moisture, but these will affect all the peaks in the spectrum to an equal extent. So you can see like all the peaks in the spectrum will be somewhat higher or lower. Whereas what we are seeing here with these masers is that you can see that the peaks vary independently of one another. So you can kind of compare them to one another and still at least qualitatively tell that something is changing.
Okay, anybody else? Great work, Edward. Keep us informed of more stuff. Let's go with Dmitri.
Thanks, Rich. Hi to all. I am continuing work about evolved star observations. Just a moment, some presentations. Interesting observations for last 2-3 weeks. This is about two old evolved stars in I observed by 20-meter dish in Green Bank. One is IRS 18450148, short name W43A, and second star is IRS 18460 minus 151. These stars radiate in hydroxyl element and have short name with OH prefix. You can see it. Both stars have water high velocity jets. But they're not. They separated very large distance and have not physically connected, not belong the same clusters. The same cluster. Very small angular separations, 0.26 degrees. But this star is radiating in hydroxyl over background of star forming region W43. So star forming regions also radiate in hydroxyl, especially in main lines. 1665, 1667 megahertz. both stars on Hertzsprung-Russell diagram is positioned there. One star is this is OH 31 minus 0.2 is about here, and second star W43A already in stage of forming planetary nebulae and post AGB star. Velocity range for this star and star forming region I have written here. Lower velocities for first star and for seconds higher velocity, and wider velocity range for star forming region W43. Few words about indicator for characterizing the star. Simple indicator mass loss rate to squared stellar radius, and it indicates mass loss, flux density, and more complicated indicator for true real envelope density is stellar wind velocity is used for its calculations. I use this indicator because the stellar wind velocity can be easy calculated if spectrum of evolved star with two peak spectrum evolved star can be detected, and the stellar wind outflow, stellar wind velocity can be calculated as the half of difference between velocity of both peak. Here is parameters of both stars. First is later stage of evolution, already forming protoplanetary nebula. These plots from Nancy telescope already fading in 1612 megahertz. Its radiation already fading, but second star is younger and still well radiating in 1612 megahertz. So these values were calculated using ChatGPT. ChatGPT can find measured mass loss rate, can estimate stellar radius, and estimate stellar wind velocities, and can calculate can make work of with parameter estimations very quickly. It's very convenient. So first star is have lower indicators already in fading its activity, fading radiations and activity, and already have lower lower flux lower flux of mass of ejecting mass, and younger star is still well shredding its gas and dust, and it have a higher density indicator and mass loss flux density indicator too. Instrumentation of observations 20 meter dish. Beamwise is about 0.3 degrees, less than stars separations, and W43 have about 1 degree of angular width, so it's feel the beam of the dish feel the beam of the dish. First observations of IRS 45 or minus 0148. This is older star. Already I don't see already any traces of 1612 megahertz radiation, 1612 megahertz activity. Its velocity is about 2644 kilometer per second, and here I don't see any hints for its activity in this band, and can be can be already dim in this belong to other do not belong to the star, and belong to other star. Also interesting deep in at velocities about 90 kilometer per second. This is absorption line, and it observed at 1612 megahertz. Possibly from this line is possibly from W43 star forming region. Observations of from when the beam is directed to this older star, you can see very interesting spectra for 1665, 1667 megahertz. Minimal detectable peak slug density is about one Jansky. Sorry, very deep line, absorption line is about 90 kilometer per second observed, and second absorption line about 40 kilometer per second. This line is with high probability is from W43 star forming regions, and you can see a wide background, as I suppose from this is from W43 star forming regions. This peak about 35, 37 kilometer per second can be from this old star, but I am not sure it. I'm not fully sure about it. Now is the result of observations when the beam is directed to second younger star. You can see still you can see two 1612 megahertz double peak spectrum with higher levels, more than we significantly higher peaks of spectrum. This is surely the W peak spectrum in 110, 140 kilometer per second belong to this younger star. Still shallower absorption line present in this spectrum at velocities about 90 kilometer per second. Next, main lines 60, 65, 60, 67 megahertz. When the beam is directed to younger star, you can see still the peaks at about 110, 114 kilometer per second. This is very interesting because it's a rare case when 60, 65 megahertz can replicate 16, 12 megahertz shape of spectrum. Wide range emissions from minus 10 to 140 kilometer per second is lower at this peak. I suppose it. I think that this is because the center of star forming region WS43 is closer to older star. Then this star, younger star, is some aside from center of star forming region W43. Summary in conclusion. Stars with small separations about 0.26 degree are observed. A strong background from this is all strong background from star forming regions 43. This background is well seen. Older star has no evidences of 1612 megahertz radiations, and this fade extinction can be. I think this extinctions can have been progressed already. A peak near 40 kilometer per second of mainline spectra probably belong to these older stars. Absorption dips. Both absorption dips at 90 kilometer per second and 40 kilometer per second belong to W43 star forming region. Observed spectra were compared with previously observed absorption data from this work. Comparison and calculations also made by using ChatGPT. Using ChatGPT, it's very convenient. Sorry, the second dip is about 10 kilometer per second. and I think it can belong to W43 too. Younger star is well seen in 6012 megahertz with 6012 megahertz double peak emissions, and its emissions in main line 6065 megahertz also have double peak emissions. Velocities are the same, and also belong, I think, is also belong to the star. This is a rare case when 60-65 megahertz have the same shape of spectrum as in 6012 megahertz in evolved stars. 1612 megahertz absorption line near 90 kilometer per second observed. It's belong to W43 kilometer 43 star forming regions. This is also a rare case because 1612 megahertz line star forming regions usually don't not demonstrate absorption line in these frequencies. And wide range of main lines, background emissions, and well seen, and have lower level when the beam is moved aside from the center of W43 star forming regions. Also, I would note very convenient use of chat GPT in calculations, collections of info about astronomical objects and data analysis. This is all for now. If some questions, I will be glad to answer.
Any questions for Dmitri? I don't hear anything. Okay. Excellent work, Dmitri. This is really good stuff. And just to let everybody... Oh, go ahead.
Okay, I will try to prepare. I will try to be in time for 12 December with some text for new journals with this work. I hope we'll be in time until next Friday. Thank you.
All right, thank you. And for everybody that's a member of Sarah, notice he's using the 20-meter dish. You can use that 20-meter dish too. We have an account, and if you get the access from Steve Zekas, you can also do this kind of level of work. And so it's very easy to use the 20-meter dish. We got a lot of YouTube videos on it. Okay, let's go to Wolfgang.
Hello, everybody. I have two things to share, essentially picking up from Edward. Edward sent a note over the news group that he saw the brightening, and we received that on I think the 24th or 26th of November. So we took the opportunity to make some observations a few days later, and let me share that. Where is it? There it is. Okay. All right. This is the spectrum of Westerhout 49, the one that Edward has been observing. And there are three curves. The red curve is a recording from early November. I think it was 4th of November this year. And then we got this notification from Edward, and we took another spectrum, which is the black one. That is on the 30th of November. And you can see there's clearly an increase. And again, to address the aspect that Bob has raised, yes, there's some uncertainty because, again, of pointing errors and also some gain drift that might have happened. But the main argument here is the same as Edward's, that we have a more or less constant in the velocity range around 5 to 10 kilometers per second negative. That stays pretty much the same, but we do see the increase in the same feature as Edward has seen in the 6.9 kilometers per second. And then we did another recording, which is the blue one, on the 3rd of December, so just 3 days later after the black one. And you can see it has already dramatically decreased. So we believe that this brightening of the 6.9 per kilometer line has occurred just briefly, and we may have just seen the decline on the 30th of November. So it may have been brighter in between. But in essence, it confirms two things. First of all, the observation from Edward was perfectly fine. We can confirm that there's a brightening of this line. And the second point is that you definitely have a high variability of Westerhout 49. I think there's another mic open, so maybe we can check that. All right, so this is number one, what I wanted to show. And then I want to pick up the subject of interferometry. I think there is nobody from the cameras team from the Netherlands present at the moment, because I really have to be very thankful to them for making this joint experiment. What we have done is that we try to see fringes or to correlate the two 25-meter dishes. We are about 200 something kilometers apart, so that's a fairly large baseline. So we did what one could call a very long baseline interferometry. And the way that was done is, obviously in this case, everybody has its own clock. So you need to have sort of an idea how much do the clocks differentiate. And we did some long-term measurement of the clock at our site, and Dringel have the fortunate situation that they are tied to a water maser clock reference, so they're very precise. And so we determined that we have a certain clock offset, which is about 5 times 10 to the minus 11. The good news is that that is very stable. While there is a certain offset, the offset doesn't change much. We use a rubidium, and that's fairly stable. So that was one of the prerequisites. The second element was that we were using identical equipment on both sides as far as the backend is concerned. We were both using B210 software-defined radios. We used the same software to collect the IQ data. And then later on offline, we did the correlation of the data. And another aspect is that, of course, you need to have the same starting point when you start the observation. We did that with the help of a PPS signal derived from the GPS satellite. So these were the ingredients, and all this is some preliminary stuff that I'm telling right now. But it was successful. We did see fringes on a couple of sources that we tried. There's another method that was used, which is called fringe stopping. So when we correlate the data during the time when we do the recording, obviously we are tracking and the telescopes move a bit. And also the Earth rotates, so the fringe frequency changes over that period of time, especially due to the rotation of the Earth. The fringe frequency is the range of about 40 hertz at that baseline. And we did the calculation to compensate for that. That is called a fringe stopping technique. Now, what I would like to do is to share one picture here. Yeah. So we should concentrate on the leftmost panel here. This is this is depicting the correlation magnitude as we vary the offset by a small amount. So there's a certain offset or a certain time offset when you get the correlation. As soon as you move away from that, the signal drops away. And that is a clear indication that you actually see that. Yes, please.
Can you maybe zoom in a little bit?
Yeah, sure. I can try that.
Easy to see. It's a bit small.
Yeah, okay. It's a small one on a big screen. So let me see how I best do that. I'll stop sharing for a second.
It's on top of the picture, the plus sign on top of the picture.
Well, I don't have a plus sign here. Yeah, there we go. Yes, that does that trick. Okay, so I will now reshare that. As soon as I try to share it, it goes back to the same scale. So try that again. Okay. Is that better?
Yeah, thanks.
Oh, okay. So again, the left panel. So that is, as is depicted below, that's the offset in steps of 10 to the minus 5 seconds. So 10 microseconds. And the vertical scale is the fringe, the correlation magnitude. This was on a source called S50114 plus 81, so conveniently circumpolar, that has an intensity of about 0.7 milliamps. So it's very, very low, but we were still able to see that in the correlation. I guess that's just a starting point. Obviously, we try to do more things along those lines. Of course, we always have to coordinate observation times between the two telescopes. But I believe this is the first very long baseline interferometry done in the amateur arena. So we're quite happy about it. And obviously, we will do more work on that and then do a careful write-up of things and exactly how we do it and report more on that. But I just wanted to bring that message across. Yes, you can do very long baseline interferometry with amateur means if you do it carefully. Okay, any questions, any comments?
I would like to make a comment that, you know, I didn't really expect that Edward's system varied very much, but I wanted him to comment on it. But the fact that you made the same observations and confirmed his data is a very powerful thing. And the fact that you did it through Sarah or through an amateur communication scheme whereby he reported it and then you confirmed it is also a very significant thing, I feel. And I think your results for this interferometry are very exciting too. I think that's a very good work that you're doing there.
All right. Any other questions for Wolfgang? Thanks, Bob. I agree with you. And Wolfgang, anything else?
Not anything more from my side. Thank you.
All right. Thank you. Let's go to Carl.
Good afternoon, everybody. Just an update on our scope in the box. We've finally received all the components and look to be able to start that project in the spring. In addition to that, our local observatory, the Custer Institute out here on Southold, Long Island, they look to possibly be donating their older, it's not used right now, but they have an older 2-meter dish that is sort of up for grabs. So that might be an additional project that I've got access to. Just it needs most of the components added onto it, but it's a pretty big dish in decent shape. So hoping to possibly put that into operation down the road.
All right. Thanks, Carl. Let's go to Preston.
Hello. I don't really have anything today, just enjoying listening to everybody. So hello, thank you for the good presentations.
All right. Thanks, Preston. Jack. Jack
Hey
Gansel.
folks, how are you all doing? Appreciate the presentations. It's really good stuff. I've been building a 1.5 meter antenna and have been experimenting with using a vacuum bagging. I'm laminating a very fine stainless steel mesh between two layers of fiberglass material over a form, and with the vacuum bag, I'm getting extremely smooth surface. So we'll see how it goes. It's an experiment, and hopefully it'll turn into something useful pretty soon. And that's really all I have.
Thanks, Jack. Paul.
Can you hear me?
We can.
Yes.
Well, I've been working, trying to see if I could create a little maser antenna like Edwards, and he's been helping me out. And I kind of gave up on my first design, which was based on this DirecTV dish, because I couldn't get the pointing and all sorts of things straight. So I have another one that I built. If you don't mind, maybe I'll take a couple minutes to show it. Let's see here if I see if I can get it to work here. Sometimes it doesn't pop up for me, so you'll have to let me know if it's showing. It's not doing it. I assume you can't see anything yet?
So black.
Yeah, unfortunately, this.
You have to select the window.
Yeah, I'm trying. Let's see here. It's this. I use Linux, so.
Did you get it?
But getting close.
Okay, Jack. Jack, we'll get back to you on when you're ready. Let's see. Let me go to somebody else here. Bill Miller.
Yeah, Rich, I don't really have anything. I was just attending for the first time in a long time. Been pretty busy. And one of the things that we're experiencing is as we put ourselves out there in the DSES organization, we're collecting a lot of stuff. And so we just got a couple of 8-foot dishes and a 6-foot dish and a 4-foot dish that they loaded into the facility today that we're intending to give to the local high schools in the rural area where we're located for an educational outreach. One of the problems we have with this is knowing what to take on and what not to. But we had an aerospace company in southern Denver go out of business or move back east, and they gave us all their stuff. So for the asking, I hear a lot of people talking about building their own dishes in various ways. For the asking, often you can find many of these organizations and people just giving up television dishes and such. You get pretty good sized dishes for nothing. And so I just wanted to mention that we seem to get more than we can use. And so that was going on today down at the site. We'll have to talk about the upcoming conference. I don't know if that's something we'd be able to do. Got some other ideas for that. We're going to discuss in our board meeting. And that's about all I've got. So I'll give it back to you.
Thanks, Bill. And DSES has a brand new building, probably name it after Bill because he did all the work for it. But and it's a new command center basically for the 60-foot dish. So it's really top notch. Okay. Let's go to Jack. Did you get your technical stuff figured out? Okay, we'll go to Al Ernst. You there, Al? Okay.
There we go.
Not hearing you, Al.
Al, we're not hearing you. Go ahead. We see your screen. Hey, Al, are you on mute? Nope, he's not on mute. Okay, Al, we don't have any audio. Boy, this is a good technical day for audio visual. Okay. Al, try to say something. No? Okay. All right, we're going to get back to you, Al, and keep going. And let's go to Conrad.
Hi. Well, my superset is working as designed, so every day I upload information to Stanford University, so I'm pretty happy with that. Over the last few weeks, I've been trying to perfect the meteor detection. I got all the equipment set up. I've had a few little software problems just because I didn't understand the software that well, but I think I've got that overcome. And there's going to be a very nice meteor shower in this month, so I'm looking forward to that. In fact, it's next weekend. And also, I did send away for the scope in the box. And right now, the purchases, I guess they're processing it right now. I'm very looking forward to getting that and start observing hydrogen line. And where I go after that, I don't know. But so far, this has been a lot of fun. Hasn't been a great season so far for optical astronomy, which is my first passion. And also being sick doesn't help at all. So, moving right along and having lots of fun. And there is a lot to learn.
Well, thanks, Conrad, and glad you're shifting off of that optical stuff. That's
oh no, it's not over. I've got a tremendous amount invested in that. I'm far from that. And I'd also like to add, I've put some questions out on the Google groups, and people have been very helpful, and I'm very grateful for that. Because without that help, I don't know what I would do.
Yeah, it's our 24/7 help desk for
it is
radio astronomy. It's unique.
It is.
Thanks, Conrad.
You're welcome.
Let's go to Bob.
Okay. I've been doing some work that I wanted to share here that was stimulated by okay, I ended up with the PC board up first, I think. But I've developed a circuit here to, okay, maybe I'm sliding that out of the way. I hope you can see my schematic diagram now. Is that right?
We can. Can you zoom in a little bit?
Let's see. No, can't zoom in.
All right.
Okay, so anyway, what it is that this is the dish antenna, and then we have here a filter, and then a switch, and this was all stimulated by Ted Klein and some comments he made about wanting to be able to have a PC board to do switching between a reference resistor, which is right here, and I added an LNA to the picture. And in addition, I've got a design for a board that I call it the control board. And this board monitors the DC voltage coming down the feed line. And when it goes to 7 volts, it switches the pin diode switch between the LNA and the 50 ohm resistor. And then I also have another board that's a remote board that would go on like a Raspberry Pi or connect to another computer system that would generate that change in voltage. And so now if I slide it back up here, you know what? The PC board was zooming in. Huh. So what I've done is I've laid out PC boards for all of these things in KiCad. And this is the RF board, and this is a control board. This is a
Okay, we can't see
shield.
that.
You
Your
can't see
screen
this
didn't
one?
change.
Okay.
If you go to the top, you'll see some magnifying glasses, like plus, minus, all the way to the left now. Go to the left on the docking.
I think that might be in Windows, but not on a Mac. I don't see any.
Yeah, when you go all the way to the very top, right there. Go to the top. Keep going up. Keep going up. You'll see like to the right now. To the right. One more. Right there. Click on that.
Yeah, that's going to get us a schematic. But I need to switch to the other sheet now.
Oh.
Okay. And I think what I got to do that is stop sharing and reshare it. Like this. Now you should see the PC board.
Yep.
Okay. So back to this is the RF board. So you can see it's mostly made up of that filter, and it's a mini circuits filter. It has a penalty of about 0.7 dB loss. And then right up in here is a real tight layout of the LNA and the pin switch. And then it's got SMA connectors on both ends. Now this board needs to be built on like a Rogers RF materials to accomplish a low loss. And the expected noise figure here is about 0.3 dB at 1420. And this board is the control board. So my idea is to take this board here, which is a shield, and place it on top of this board first, and then lay this control board on top of that and make a little sandwich. And built into this board is the power supply. Now, this RF board would become fairly expensive because, like this filter, for instance, it's about $70 just to get the filter. And then the PC board material will drive up the cost as well. So some people that might not want to spend that much money may opt to just utilize this control board, and it's got a relay that sits up in this area right here. This is the control contact for the relay. And then you could use the contact closure on this to switch like the NOALAC board. Ted mentioned that it has a pair of contacts that if you short, it brings in a 50 ohm reference. So this could be utilized in that way and not even pick up this RF board. Although one of the reasons I did this board is because you have been having trouble getting the NOALAC preamps. And so that would circumvent that problem. And then I laid this board out so that it's a top hat for a Raspberry Pi Zero, or it would also plug into a standard Raspberry Pi 4 or 5, which people have also used for radio astronomy. And so its main purpose is to just switch a supply voltage on and off that's going to feed out here and give it the proper voltage level to operate either the relay or the pin diode switch. And I'm going to probably prototype these boards and just prove them out, although some pieces of it I have already built in the past and I know they'll work. But I'll be putting this up on GitHub pretty soon. I've got these little small boards that I'm going to build this is what I call a DC injector, so that the voltage that's created over here on this Raspberry Pi board would feed into this board here with two SMA connectors to get it into your feed line to send out, and it gets picked up over here and separated by a blocking cap and fed over to the control board. So one of the challenges here is to try to maintain a 50 ohm impedance in this system, and with cheap PC board material like FR4 you need like a 3 millimeter wide trace. So I'm going to experiment with a couple of different options here and just see how much of a hit we might take with this little board here due to using inexpensive materials to try to keep the cost down. Okay, so I'm going to put this all on GitHub pretty soon, and I'll note that I did. I sent a copy of it to Ted, but I haven't heard back from him yet. Any questions or comments?
All right. And for Bob? Okay. Thanks, Bob. Good stuff. Dennis.
Okay. Can you hear me?
Yep.
Yeah, like you say, great stuff. I really appreciate what Bob's doing with those boards and all. Anyway, I don't really have anything new to offer here, but I'm really enjoying what everyone's putting on, and it looks like Al may be ready to display his or give us these audio. Go ahead and let's have it back, Rich.
All right. Well, good, Dennis. Good handoff to Al. That's a new.
All right.
Go for it.
Am I coming through now?
I can hear you.
Ah, great. Okay. So I was just saying before that one of the things I did last year was build an 8-foot dish, and that went together pretty easily. It took maybe about 3 months to put it on out in the backyard and get it working, and I had some good observations with it. So I got encouraged to make something larger this year, and I decided to go with like a 12-foot dish. So here's an 8-foot dish, and 12-foot, is going to come out a little bit further than that. And we got something that's going to be much larger. Actually, I didn't really anticipate how much more difficult this would be. It took quite a while to do it. So it all started in the garage. And
wait 1 second, Al. Are you gonna display your presentation?
Yeah. Is it coming through?
No.
Oh. All right. Let's go back again to here. Well, so we're not seeing anything?
No, you got to share it.
Oh, I didn't. Oh, I know what it is. Okay, now I turn it on then. Okay. And, share. Okay, we sharing now?
Yep.
Okay. So anyway, let me go back to this one. So this is the 8-foot dish I built last year, and I'm building a 12-foot now. So we get a kind of an idea of the scale of the difference and why it would be so much more difficult. In any case, so I got to this point of assembling it in the garage, and my whole point of doing this is to do it as inexpensively as possible. So I scrounge around a lot, and whenever I find something, I put it aside for later. And for example, in this case, this whole base here, which was the base of the dish, was from a football program scaffolding, where they had used this to put their video cameras on and be above the crowd, but they threw it away. And I guess they paid, $1,500, $2,000 for it, but the school didn't want it, so I said, okay, I'll take it. And that became the base for the dish. So this would be the declination. It's a transit instrument, so this is the declination here. Anyway, so let's go on. So I began assembling it later in the summer when the sun got a little bit more tolerable outside here. And so we can see the struts, they're all bent properly for a parabola, and they will all attach with additional support beams that go down to the main axis. So we can go a little further. And this is about 3 weeks ago when I began to put the mesh on. And again, I'm trying to be as economical as possible. It would be nice to have, proper mesh, but I just went down to the hardware store and bought some aluminum screening, which, by the way, comes in a nice gray now, so it's not as conspicuous in the neighborhood. But you can see these struts coming down to the main axle over here. And if we go in close on that, you can see kind of like the way the whole thing is arranged. It's not really on axis, so I have to use a counterweight to make sure that things are in balance. And this worked out really well. I was originally thinking I would build a different kind of main axle here, but this worked out pretty well, just having the counterweight and then using a gusset plate to affix the the two axes perpendicular to each other. And after I got the mesh on, this is basically what everything looked like. And I was ready to do some basic testing at this point. It is a transit instrument, so it's all I need to have is a something to indicate the angle, and it's not motor driven. I have to go outside, but it only takes about a minute. It only takes about a minute to actually change the declination. And I had this old setting circle from an optical telescope, and I just adapted it and put it on, and put a little strut out here to indicate the angle. And as you can see, I mean, this is the about 4-degree beam, so it's adequate to point, pretty well within that path. So I went out a few minutes ago to take another image of it. So this is what it looks like this afternoon, and it's not completely done. Things like this are, I guess, they're never really done, but it's pretty much assembled, I guess, 95% anyway. So up here is the LNA, and there's a coax line coming down through here, which is kind of unreliable now, I guess mainly because the connectors were kind of cheap connectors, and I need to replace that line before I do anything serious with it. But I have done a few shakedown runs on it. So, looking up here at this is, going into the Milky Way at around 10 degrees, and then looking at IF average down through that, we can see the changes that occur. And then I did another shakedown run here, a little further up in Cassiopeia, and the signals are coming in there too. So I think that basically it's working, and I'm hoping that I can get some decent observations in the future. And that's about what I've been doing here.
All right, anybody have any questions?
Great work. Yeah. I can tell I also have a 3-meter dish that's also just a transit instrument, and it works really well at 1420 megahertz, so no problem with that. I was wondering though, what are you using to hold the feed in the focal point?
Let's see if I can go up to that. Yeah, so what we have here is a 2-inch pipe. And then this over here is a PVC pipe. So this can slide down inside this, and I can bring this out to change the focal point. So that there's a little, like a bushing that goes around here with set screws in it. So I can just move it in and out. And so what I do basically is I look at IF average and zero it out, the frequency, and then move this, and then see how it changes. If the IF average drops down, if we get a dip, then we're getting worse. If it comes up, then it's somewhat better. So when I did this, I was off by maybe about 1 centimeter from the design frequency, design distance, but it seems to be pretty good right now anyway. I'm interested in what you're doing there, especially with Andromeda, which I think you were going to mention a little bit more about.
I have a question about the feed design. Do you have a resource that you used when you designed that part of the dish?
Okay, the feed is a loop feed. So let's see if I can just bring it down here. So there's a loop up. I should maybe have an image of that, but if you can imagine the loop going around here, and then there's a little bit of tiny coax coming in here, and then that goes to the LNA inside here, and then to the coax. So the coax attaches inside here and then goes down through the tube. So the loop feed seemed to work pretty well. There's some people at our club who have tried other kinds of feeds, and they have had difficulty with them. but this seemed to work pretty reliable.
Yeah, it looks like a great design having it slide through the center point to really fine tune the feed. It's a great innovation.
Yeah, what inside here, the PVC goes down quite a ways inside here, and then at the other, right around in here, I have another bushing, so it keeps everything centered, so it can slide back and forth pretty easily. It works pretty well. Okay.
That's fantastic work, Al. That's a great candidate for a linear actuator to move the elevation portion of it.
Yeah, if I knew how to do that, I might consider it.
It wouldn't be difficult.
No? Okay. Maybe you'll have to give me some ideas.
Okay, we can do that offline because I can see where you can put a linear actuator, like a 36-inch or 30-inch linear actuator in the elevation bar.
Okay.
What you call the declination bar.
I would take a look at it.
Okay, any questions? Al, this is really good. Can't wait to. Now, what are you going to use for software to collect?
Well, I'm using IF average right now.
All right.
And I make CSV files and then do some processing with that later on.
All right. All right. Looks like you're well on your way. Thank you.
Okay.
Okay. Let's see, Pablo.
Yeah, not much to report. I have 3 operational radio telescopes, 2.1 meters and 1 70 centimeter, which I'm going to try to improve. Alex Pettit is helping me with that. Just put a little extension on it, and then I'm not producing any science. I'm at the IF average stage, but eventually I'm going to go to Ezra on all 3 and try to correlate the data. I'm able now to control the elevation remotely using a linear actuator, and for the measurement of the angle with motion sensor, that it's pretty accurate actually, that I've attached to the dish. So I'm able to move the elevation, but not the azimuth yet. I have to engineer that. I did engineer it, but I have to get a better motor that's going to withstand the Santa Ana winds here in Southern California when they get here. But and then eventually I'll produce some science. But that's basically it.
Okay, thanks. Any questions for Pablo? All right, Adrian.
No, I don't have any. I don't have anything for today, and just enjoying the presentations. Kind of, excuse me, a bit under the weather here, so it's kind of kept me out of doing much of anything lately. But yeah, some great presentations today. I really enjoyed it. Fantastic.
All right, get better. Paul, already get you?
Yeah, I was going to try again if you.
Go ahead.
Try to set up differently here. Let's see if this works any better. All right, let's see. Something happening.
All right, you guys see it?
Can you see it?
Yep.
See it.
Okay, good. I don't see it on mine, yes, but that's fine as long as you can see it. It says hybrid optical radio telescope. That's what's showing for you. Okay. All right. So what I was trying to do is to make a little telescope like Edward uses for doing masers and things of that sort. So my second attempt, I tried using a DirecTV dish, and I had a lot of problems with that off-center design. So I got another dish, and you'll have to let me know the way I'm scrolling here. Is this showing up on the screen when I scroll it? Yep.
That's good.
Okay. All right. So I got a 4-foot dish from eBay. That's a center mount design of a one of these satellite TV dishes, and I built something to hold it to my computer-controlled tripod, and something to hold the LNB, and also a guide scope. And what I do is I use optical plate solving techniques with sharp cap to position on things. If you see on the upper left side there, you can see that little red and black thing. That's the guide scope and camera. And I made it so that I could actually interchange the detectors. So I can, on the upper left side there, you can, if you actually see the little silver dish, that's it's like a 6-inch pie plate detector with a loop in it. For I have a 1.4 gigahertz and 1.6 gigahertz version. And then the more interesting one is on the right top side. I have a bullseye LNB, which will operate in the 10 to 12 gigahertz range. I think that's what Edward has successfully used. So I'm, in early stages of trying to make sure that I'm actually getting decent signal to noise and so on this. So if you can see, I switched to the next picture. So one of the other things I wanted to deal with was I had my electronics was very close to the antenna, and I didn't like that. I was afraid of RFI problems. So I had to go through some gymnastics to be able to move it away. I had some repeater kind of technology, but it seems to be working now. I pointed it at an area that I've used before for calibrating dishes, and this is pointed in a Cygnus A area, and this is, if hopefully you can see it okay, this is the recording I got just for test purposes. So that was working with the loop. And then I want to do some measurements to make sure that running this further distance was good. And also in operating the bullseye, you have to feed it 13 volts and actually have to feed it at 22 kilohertz tone so that I can switch the range. If I want to use 12 gigahertz, I have to feed it a tone. I have this little device that is a satellite finder that is good for feeding in the voltage and the 22 kilohertz signal. And that has to go into a bias T in the upper center of this image. You can see that little square thing. That's the bias T. So when you put it all together, I was getting about 5 dB of loss. I used a VNA to measure that. You can see on the bottom right side is my VNA. So I'm getting about 5 dB of loss, which I guess is fine. We can overcome that with the SDR gain. And so the other thing is that I was worried about was because I'm trying to get down to some much smaller signals, I was particularly worried about temperature effects. So I did some experiments, and I have a Peltier cooler. If you can see the upper right, there's a picture of those are some SDRs I have mounted on a Peltier cooler, and I use this IR gun to measure the temperature. So that's how I created the diagram to the left. I was sampled at some points in time while I was recording with IF average, and the blue line on the bottom is the gain. It's actually times 10. So what it says 10 on this scale is actually 1 dB. So I measured the change in gain, and it was over the range that I tested. It was showing me about a 2.5 dB change. So it can be pretty significant with just about a 20-degree change in temperature, which can happen just from warming up or because of the ambient temperature that you're operating in. So I was, wanted to make sure I had that under control. And then I also wanted to see with this dish, as I tilted it, what am I picking up in terms of the background levels of activity? And the blue line shows some measurements that I made with the dish, tilting it from minus 20 degrees, which as far as I could point it down towards the ground, up to about 80 degrees or so, which is as high as I could get it up in the sky. And you can see that there's about roughly a 4.5 dB difference between the best I could do for ground versus cold sky. What I did was I took the L and B off, and then I pointed it at the sky and pointed it at the ground. The red line shows the difference. It's more like 6 dB if I have it really pointing directly vertical and really pointing it at the ground. So again, I'm just trying to characterize this. I'm not at the actually recording a maser yet. I'm just trying to get to the point where I believe that this antenna system can do it. This just shows kind of a bigger blow up of just looking at the cold sky from the standpoint of what the antenna was able to be configured for versus the ground. And so the difference in that operating range was about 0.4 dB for me. So that was, my reference for how much effect I would have depending upon where I was pointing. So I did a drift study, about a half hour. In the middle here is where the sun was centered. I was trying to actually put some pictures on here from what I had photographed, but I actually just did this work yesterday, so I wasn't able to get the optical images aligned with this yet. Maybe another day I'll show that. But so this is showing the antenna behavior with the drift, and it's about 5 dB between my version of cold sky, which was running about 15 degrees. I think it's about 7.5 degrees off from the center of the sun. What I tried to do from this, and I'm not sure whether this is really convincing data or not, I tried to see if I could validate the beam width of the antenna. The theoretical beam width for it, based on, it was like 18 inches focal length and 4-foot antenna, is about supposed to be like about 1.5 degrees. And by doing this drift study and measuring when the sun went, how it responded to the sun in terms of the gain, and trying to fudge the sun diameter, which is about 0.5 degree, I get a rough estimate of about 2 degrees beam width doing it this way. So it's in the right ballpark. And you guys can tell me if this is an unacceptable way to do it, but I thought it was an interesting thing to try. So then I went to try to do the moon, which is the sun here is, like I said, it's like about 5, was closer to 5 dB. Well, sorry, this diagram is misleading because this isn't really calibrated right. This one is. This was, like I said, about 5 dB. And so then I did the moon, and not surprisingly, the signal is much smaller. And this is when I referenced the moon's maximum versus being about 7.5 degrees off from the moon, I got a measure of about 0.1 dB difference. And Edward I looked at his, I was watching his video. He's pretty much everything I do is based on his work. That he got closer to, I think, about 0.3 dB. And so I was looking at, I replotted the data, putting an extra point in, which was actually pointing at the zenith. So you can see here what it's sitting on top of. The moon, actually, if you go down and see this, was pretty low in the sky. This is from Stellarium. You can see that it's really pretty close to the horizon. It was only about 25, 26 degrees above the horizon, which is not a great place for me to have to record at. And so I figured, okay, let me recalculate it. What I did was I took the actual, the zenith measurements, and I subtracted that from my drift data and replotted it. And here it looks like it's closer to 0.4 dB difference. again, you guys maybe can correct me if my thinking is wrong about viewing it this way, but I think that the poor signal separation is due to the fact that the dish is pointing pretty close to the ground, and this little inset to the middle right here shows that the difference between pointing the dish as far as I could to the zenith versus being at pointing as close as I could get to the ground, which was only 20 degrees, that it was about 0.4 dB difference. So this was, it kind of makes sense, I guess, that my measurements might have been washed out a bit by the fact that the background was high. Also, there's on the left, there was this little bump there. I didn't know what that was. It must be some kind of an artifact. I thought it might be a satellite or something. But what I did was to plot a waterfall of the data so that I could see the individual traces. The way that I made these diagrams was by taking the average over the entire spectrum, which was centered on about 10 gigahertz. But this is what the actual individual spectra looked like. The offset here is artificial. I just stacked it so I could see it, but I don't really see anything. It's not like I see any kind of pattern that would indicate that a satellite went over or anything. So I'm not really sure what that little hump was. So I guess in conclusion, I think I'm getting close to being able to consider looking at a maser, and I figured I'd present this and get feedback and see if anybody like Edward, for example, had any suggestions of what else I maybe should do to tune things up a bit. Okay, back to you, Rich.
All right. Wow, you're really getting far. Good work. Edward, did you have any comments?
Well, good work. Looks promising. So yeah, I was just looking at my own moon data that I recorded some time ago for that video. So that was also recorded at a fairly low altitude. So the moon was also only about 30 degrees high up, but maybe your dish has just a somewhat different pattern of side lobes. I don't know. So, but so far it looks promising. So, yeah, one thing I was thinking about the variations of the gain of particularly the SDR with temperature. So there's also something that I'm paying attention to. So this is more problematic when you're doing continuum observations of weak sources. So looking for essentially the change over the entire spectrum. So yeah, for the moon, this would be somewhat important, although the moon is still like not that weak. For spectral work, it's not as important, like because you're essentially looking like a small portion of the spectrum that has a higher spectral power than other parts of the spectrum. So variations in your baseline do not matter that much. Still, I have my SDR usually mounted on a big block of aluminium with a fan from an old computer to cool it down a bit. So anyway, it looks good. I hope you can capture the methanol maser in W3OH.
That's what I'm aiming for. That's what I'm aiming for. And by the way, what I did was I was checking the temperature of the SDR with that little gun, and it was staying I think around like 54 degrees plus or minus maybe half a degree or so. I can't measure it that accurately, but it was fairly stable during the observations.
Yeah, then we'll probably be fine, I guess. We'll see.
All right, any other questions? Great job. Let's go to Bruce.
Let's see, yeah, I think I'm getting in here. Okay, well, on Bob's presentation, I had some comments and it thought I'm a little bit too late, where he's got the preamp and the switch and the load resistor. back probably about 20 years ago, I did a Dickey switch receiver, 408 megahertz, using 50 ohm load as a reference. And before I could make the thing work decent at all, I ended up with my 50 ohm resistor, one of the little SMA terminators, and put it inside of a little oven that was made for keeping quartz crystals at constant temperature and two-way radio equipment. So the resistor was at a constant 50 degrees C, and that made a considerable difference in how well behaved the Dickey switch receiver was. So that is something to think about, is ambient temperature affects moving the thermal noise out of the resistor around on you. So that is something to think about anyway. And the other thing I wanted to comment on is I'm still doing my study of noise from Zener diodes and trying to establish a good noise source for calibration. But one of the things I ran into, I got one of those little tiny spectrum analyzers. I got the ultra version that goes out to 800 megahertz direct measurement. And before that, I've been using an old HP 141 spectrum analyzer with a storage tube that's going to die one day, I'm sure. But anyway, the Tiny SA, it actually seems to work somewhat better for the purpose of analyzing noise. The problem is I had real hopes that I could get the results on the screen off to a CSV file so I could work with them on the spreadsheets in the computer. And I've had very bad luck with that. So I wonder if anybody's had experience with the Tiny SA family devices and hooking to a computer program and actually getting files you can run into a spreadsheet. So with that, I'm going to let it go, and hopefully somebody else has some comments on how to get along with Tiny SA, because like I said, it seems to be a good instrument other than computer interface doesn't like me.
All right. Any question for Bruce?
Silence. No one else has had experience with trying to, hook that instrument up to a computer. Then I said it seems to be a great little instrument. The only thing is that the one big advantage I thought it would have over the older stuff is, hey, the computer could hook to it, and well, not getting there.
Yeah, we did hook a Tiny SA to a computer. I don't know exactly the details, but we found it unstable. So it worked for a while, and then the connection stopped. So we were not happy with it either.
All right.
Okay.
All right, thanks, Bruce.
Seem to be having some of that same thing of it, not staying connected and other stuff there. And, like I said, when it's just used as a standalone instrument, I'm quite impressed with the performance. Much better than the old 141T, which is probably as close to as old as I am. I don't know. But anyway, been around a long time. But anyway, so that is interesting that I'm not the only one that's had trouble with computer connection. Thanks, Wolfgang.
All right. Thanks, Bruce. Flavio. Flavio, are you there? There you go.
Yeah, Doc Russell, thank you so much. Good to be here. Just a newbie, got a dish, trying to see how to put a LNB on to get some background, but just learning, that's all. Thanks, Doc.
Great. Welcome. Jack Gansel, are you back? And you try again on your just.
Yeah, I already gave a short report. I know that Paul was having some trouble. And I think there's a mix-up between the two of us.
All right. Okay, thanks. Let's see, did I miss anybody? All right. 2 weeks, we'll be doing the Drake's Lounge. I'll try to get the journal out here before the end of the month. And everybody have a good holiday. All right. Thank you. See you guys.